We have a null hypothesis. We have an alternative hypothesis. We have a critical region. This is where the set of outcomes for which the null hypothesis will be rejected. Right? The size of the critical region, the size or level of significance, is the probability that we reject the critical region, even though that we reject the null hypothesis, we're in the critical region, the outcome winds up in the critical region, even though H0 actually is true. The power is the probability that we accept the alternative hypothesis in favor. We reject the null hypothesis in favor of the alternative hypothesis, meaning we're outside the critical region. We're in the complement of the critical region.
Oh, yeah.
Okay? We've so far only really been focusing on simple hypotheses, and today we're going to get to what you do for complex. I keep going from simple to complex. To composite, thank you. I keep saying convolved or complex. Composite hypotheses. Okay, so we'll get to composite hypotheses in a second. What is the likelihood of an outcome? Likelihood of the outcome that you see given H0, likelihood of the sample, outcome given H0. This is, well, H0 tells us, at least in the case of simple hypotheses and not composite hypotheses, H0 tells us exactly what the distribution is. So what's the probability that we see x1 through xn? So that product is the likelihood of that outcome. Similarly, L1 is the likelihood of the outcome given H1, which is the same product with H1s. And so in terms of these likelihood functions, what is alpha? This probability of the critical region given H0. It's the integral over the critical region, that's our set of outcomes, of the product of densities given H0. In other words, the likelihood of this outcome is exactly this integral. Does everybody see that? So C might be you reject if you see fewer than 14 trials out of 20. Assuming that you indeed saw this outcome. Yeah?
Actually, I take that back before. Beta, I thought 1 minus beta was supposed to be the power.
Sorry, power is 1 minus beta, exactly. Beta is this. Thank you. 1 minus beta is what we will call the power. And you'll see, we'll do the power function today where you'll see exactly why you want this function for power. Beta is a measure of the power. There's a simple function of beta which gives you the power. Okay, that's alpha. Beta, or 1 minus the power, I want to measure the complement of the critical region. And with weight, so that's the probability of the complement, assuming that the distributions are given according to what the alternative hypothesis says they are. Juliet.
Is beta the probability of? Like,
beta is the probability,
oh,
and 1 minus beta is the power.
Oh.
So we want this probability to be small. We want this probability to be small. You want to say that a test has large power. Beta is going to be a number between 0 and 1. So 1 minus beta is also a number between 0 and 1. And you want this to be large when beta is small. Okay? Dylan.
What is the symbol above the x? The L0?
This, it's a vector. Vector symbol.
Oh, okay.
So this is a shorthand for dx1 through dxn. And this is a shorthand for x1 through xn. Okay, so we got our sample. X1 was equal to little x1, big X2, the random variable, was equal to little x2, and so on. we measured the probability of each, we measured the density of each of those outcomes, and we integrated that density over the critical region. Or if it's this is the same thing for discrete random variables where this is a sum instead of an integral. Right? Sakina, this is okay? And what am I going to put here? So beta is an integral over the complement of the critical region. And then I have to measure it with respect to the probability that that happened, assuming h1 is true. Does anybody know what I'm going to write here? L1, exactly. L1 of x dx. Okay. All right, then we had our Neyman-Pearson lemma. We got all the way down to the end of the proof, and then there was no actual mathematical mistake. It was an interpretive mistake in what we said at the end of last time. So, because we were rushing. So what is the lemma? Let C be a critical region of size alpha, and assume, in testing the hypothesis, so in testing the simple hypothesis, some parameter is equal to one value against the alternative simple hypothesis of the parameter being equal to the other value. If we don't have simple hypotheses to test, we're going to discuss that today. But when we're testing simple hypotheses, we can just use the likelihood functions of those two hypotheses and assume two things. For every outcome in the critical region, the likelihood of that outcome, assuming hypothesis 0, is at most some constant. So assume there exists some constant for which in the critical region the null hypothesis likelihood is bounded by that constant times the alternative hypothesis likelihood. That's assumption 1. Assumption 2, for all x outside the critical region, that ratio flips. Okay, so these are two assumptions on the critical region, and given our two hypotheses. Assume that in the critical region, the likelihood of that observation is, assuming the null hypothesis is bounded above by a constant times the likelihood of the alternative hypothesis, and in the same constant, when we don't reject the null hypothesis outside of the critical region, the likelihood of the null hypothesis is bounded below by the same constant times the likelihood of the alternative hypothesis. So if this bifurcation happens exactly along the boundary of the critical region, then this critical region is a most powerful region of size alpha for this test. In other words, for testing H0 against H1. What does that mean it's most powerful? i.e., if D is another critical region of size alpha, okay? In other words, the integral of L0 over D also comes out to alpha. And what you should be thinking is, we talked about this last time, the critical region might look something like this, and then the alternative region might look something like this or whatever. The other region, the other critical region. So both of these regions have integral alpha against the probability density. If D is another critical region of size alpha, then the power of d, in other words, the integral of the complement of d on L1 will be bigger than the complement on L1 of the critical region C. So if this error is larger than this error, this is the size of the type 2 error when you test D versus the size of the type 2 error when you test C as your critical region. If that's true, then the power, then C will be more powerful because it's 1 minus beta. So 1 minus this thing is bigger than 1 minus that. Is that clear? So that's what we're trying to prove. We're trying to prove this inequality for a D that has size alpha. And the proof is 1 line. Oh, depending on how long your lines are. It's a slightly long 1-line proof. Is the statement of the lemma clear? We saw last time how to use this to show that if you have a normal sample with known variance, let's say variance 1, then x bar is the best region, x bar being bigger than something, where that's something we know how to solve for that something that we did the class before, to get size alpha critical region. So x bar being bigger than something is a best critical region, is a most powerful critical region. Again, these are just words, so if I'm saying words you don't understand, please stop me. Taylor, is the statement of this clear?
I'm sorry, can you repeat that?
Yes. So,
No, I mean, can you repeat what you just asked me?
oh, what I just asked is the statement of this lemma clear?
Yeah.
Yeah, okay. Sorry, I put you on the spot there.
Can you
Juliet.
actually repeat the statement?
Yes, let's repeat the statement.
I
Phi,
just didn't know what it said next to the K is greater than 0, the symbol.
oh, if there exists,
Okay.
sorry, this means there exists. If there exists. Assume there exists. I just want to know, is there some constant? I mean, you can think of the constant as being 1, but it doesn't have to be 1. It won't in general be 1. But just think about the inequality flipping right on the boundary of the critical region. If the inequality of likelihoods flips right along that boundary by a constant multiple, then that's the best critical region you could have, most powerful. Juliet, you wanted me to state it again. Okay. So we have a critical region C. It has size alpha, meaning the probability of a type 1 error, assuming that H0 is true, is alpha. And that's like integrating, so you decide what your critical region is, where you're going to reject the null hypothesis, and you integrate the likelihood function along that region. That integral comes out to alpha. But there could be some other likelihood, there could be some other critical region, so that the integral over the tail this way is also alpha. Which one of these is more powerful? Well, I don't know which one of these is more powerful. I mean, I can compute the power of each of them and check. But actually, we have a lemma that says, assume that some condition is satisfied, we'll get to the condition in a second, then I know automatically that C is the most powerful region possible of size alpha. So if I have some other region, then its type 2 error is larger than the type 2 error when you use C to reject the null hypothesis, as opposed to using D to reject the null hypothesis. What is that condition? It's that the ratio of the likelihood functions flips from being below some constant k to being above some constant k, exactly on the boundary of the critical region, C. Okay? Does that make sense? All right, let's prove this. Running a little low on time. Okay, let me leave this here. All right, so what we know, so proof. We got almost to the bottom of the proof last time. What we know is that the D, this other critical region, also has size alpha. So alpha, on one hand, is the size of the critical region of C. So what is the critical region of C? It's the integral over C of the likelihood L0, right? We said that up here. alpha is the integral of c of L0. Right? L0 means H0 is true, the null hypothesis is true, but we rejected it, so we're inside C. So that's the probability of a type 1 error. For the same reason, if I integrate the likelihood over the region D, well, that's the size of the region D, and I assume that both regions have size alpha. The next little bit of the argument was to look at the set of all possible outcomes. Here's my critical region C, here's my critical region D, and then let's break D into, so the integral over D is the integral over D intersect C plus the integral over D intersect the complement of C. So you can integrate D intersect C is this little inner loop, and D intersect the complement of C is this loon. And if you add the integrals over these two things, that's the same as just integrating over all of D. For the same reason, I can break the integral on C into the integral on C intersect D plus the integral on C intersect D complement. Bless you. And the thing that I'm integrating in both cases is the same, it's L0. But I have an integral of D intersect C of L0 on the left side, and I have an integral of D intersect C on L0 on the right side. In other words, this integral is the same, because on both cases we're assuming the null hypothesis, so we're integrating over the likelihood of the null hypothesis, L0, which means that I can cancel this from both sides, and I'm left with the fact that the integral on this little loon, which is C intersect D complement, is the same as the integral on this loon, which is D intersect C complement. Does everybody see that? So I'm just canceling this and this from both sides. So the integral of L0 on D intersect C complement is equal to the integral on C intersect D complement of L0. Does everybody follow that step? Now, inside C, what do we assume inside C? That the likelihood, C is where we want to reject the null hypothesis. Where we want to reject, this likelihood is bounded by a constant times the likelihood of the alternative hypothesis. So L0 is bounded by a constant times L1 when we're inside C. That was assumption 1 on the critical region. Our assumption on the critical region is when we're in the critical region, L0 is bounded by a constant times L1. When we're outside the critical region, when we're in C complement, L0 is bounded below by the same constant times L1. So this is bounded below by the same constant times L1, now integrated over, well, some region that's inside the complement of the critical region, C. So now we've used both assumptions on C. We've used the assumption that inside C, L0 is bounded by constant L1. We've used the assumption that outside of C, L0 is bounded below by a constant times L1. But this is a constant, so it pulls through the integral, and it's the same constant, so I can cancel it on both sides. That means, so I cancel k on both sides, and what I'm left with is the integral over C intersect D complement of L1 is bounded from below by the integral of L1 on D intersect C complement. We've already gotten exactly this far last time. Then I added the integral over L1 of D intersect C to both sides. And I got an inequality that didn't help us, didn't tell us anything. It told us what the integral of C over L1 is. We're not trying to get the integral of C over L1. We're trying to understand, to prove our lemma, to prove this Neyman-Pearson lemma, we need to understand type 2 errors. A type 2 error is if the alternative hypothesis is true, but we're in the complement to the critical region. We don't reject the null hypothesis. So this is what we need to measure. So what should I add to both sides?
CC and DC.
Yeah, let's look at this. Let's look. I'll redraw this Venn diagram here. Here's omega again. Here's C. Here's D. I want to understand the integral of L1 on D complement. D complement is all of this. I understand it on D intersect C complement, or rather C intersect D complement. In other words, let me just do the trick, and you'll see in a second why this will work. What I want to add to both sides, I'm going to add the same thing to both sides, and that thing is the integral over L1 on D complement intersect C complement. D complement intersect C complement. So I just added the same thing to both sides. That does not change the inequality. If I integrate L1, on D complement intersect C complement, where's D complement intersect C complement? D complement is everything outside of D. C complement is everything outside of C. So where's their intersection? Nikki? Outside of both of them, right? This means I'm not in D and I'm not in C, so that's everything outside this thing. So that's that sum, summed with C complement intersect D. C complement intersect D. So inside D, but outside C. That's this loon. So if I integrate over this whole region and this loon, that's the same as integrating outside all of this. In other words, it's outside of C complement. Think about it another way. I have C complement on,
or and not D.
yes,
It's all C complement.
it's C complement and D, or C complement and not D.
So of course it's.
So it's just C complement.
Okay.
Does everyone other than Zach see that? I'm trying to show you pictorially, but symbolically it's even more clear. C complement intersect D, C complement intersect not D. Well, in either case, you're integrating over C complement. That's the size of the type 2. That's the 1 minus the power. The size of the type 2 error when you test C. And let's look at what I have here. D complement intersect C, and D complement intersect C complement. Oops, there's an L1. So it's D complement, and either C or not C. Well, those together tell you just it's all of D complement. Does that make sense? And that's exactly what we were trying to prove. They're on other sides, and the inequalities are the other way around. So these two statements are indeed those two statements. Mona, it's not okay.
No, I'm fine. I just looked at the big yawn.
You just what?
I just yawned.
Oh, okay. Okay. It makes sense?
No, yeah, that makes sense.
Everybody's happy with this lemma? All right. So this is the size of the type 2 error. This is the size of the type 2 error when testing using D. And C has a lower type 2 error. In other words, a larger power. And this was for any D. We knew nothing about D other than it's a critical region of size alpha. If that's true for any D, then C is a most powerful critical region of size alpha. Okay? All right, let's move on to. I was hoping this proof you guys would like, but I can see from your faces you don't like it, and I'm not sure why. Maybe it's just too many symbols.
I like it.
You like it? Okay, thank you, Ernest. Ernest likes it. But maybe let's move on. I mean, look, I'm not going to. You should understand the statement. you should understand the statement. If that proof was a little too many pieces to chew on, like I said, this is not a proof-based course. I'm not going to quiz you on proofs. But I would hope you would want to, for your own kind of knowledge, understand the proof, because it's really, it's very elementary. There's just a lot of symbols floating around, and you have to sort of do it a couple of times at home on your own when you can sit there and argue what each symbol means. Okay? All right, let's go. So what do we do with composite? What about composite hypotheses? So again, we were testing one hypothesis against another, so it made sense that there's one likelihood function, and one likelihood function for the null hypothesis, and another likelihood function for the alternative hypothesis. But really what we want to test, let's go back to, let's look back at our example. We can really keep working with this. Our example was 20 coin flips, and k, we're going to test if k, our critical region was if k is at most 14, because that's going to test the null hypothesis. So our original null hypothesis was that the coin flip, you guys remember this example from a couple lectures ago? Should I remind you what it is? I mean, I'm reminding you what it is now, but we had like some drug which had an effectivity of, or people on their own got the disease with probability 90%, and we wanted to test that the drug had, drug reduced that to 60%. That's because we were doing simple hypotheses at the time. What you would really like to test is a more composite hypothesis. How about the probability that H0 is at least 0.9? And the alternative hypothesis, now let's really take it to be the negation of the null hypothesis. So does giving someone this drug reduce the chances that they get the disease, as opposed to not, which seems to have this kind of a shape? Okay? So this is a composite hypothesis because I don't any longer have an exact likelihood function, but I do have likelihood functions for each possible theta in the list of thetas consistent with the hypothesis. Let me write that down. So we no longer have a likelihood for all of H0, but we still can compute the likelihood of theta for all, we'll write it like this, for all theta in H0. In other words, for all values of the parameter consistent with H0. So for all values of theta bigger than 0.9 in our case. Is this symbol okay? This means for all. This is for all. So here's what people like to look at to try to analyze how this test looks. People like to look at the power function. The words power, size, significance, they have like 4 different uses that are not all quite the same in statistics, unfortunately. So I need to define the power function. The power function, usually written pi of theta, of a test of H0 versus H1 with critical region alpha, critical region C, is the following. So here's what you do. So let me just define it. Pi of theta is equal to either, if theta is consistent with the null hypothesis, then it's the size of the test, assuming that. All right, let me give you the definition, and then we'll see how it works. I'm just gonna write it, and then I'll explain what's written here. So it's either the size or the power of the test, depending on if theta is in the null hypothesis or if theta is consistent with the alternative hypothesis. Let's do it for this example. Okay. For alpha in H0, in our example, what does it mean? I said alpha. For theta in H0, what does it mean that theta is in H0? Which thetas are in H0 in our example, other than Ernest? Taylor.
That they're bigger or equal to 0.9.
Exactly. H0 is that theta is bigger than 0.9, i.e. theta is bigger than 0.9. What would we do to compute the power function? We compute alpha. So what is alpha of theta? In general, what is it in general? It's the probability of a type 1 error, right? Probability of a type 1 error. Or alternatively, it's the integral over the critical region of the likelihood, assuming that value of theta. So what is it in this case? Remember, our critical region is k is less than 14. So we assume we saw a k that was less than 14. Where theta is equal to some theta, whatever it is, but it's bigger than 0.9. So in other words, if we saw a k that's less than 14, that's a sum of k from 0 to 14, k that's at most 14, less than or equal to. And then what is the likelihood function of that particular outcome? We flipped a coin 20 times, and we saw k heads. Yeah, 20 choose k. Theta to the k, 1 minus theta to the 20 minus k. That's alpha of theta. Right? The size of the test, what's the probability that we made a type 1 error, assuming the parameter really is theta? It's k goes from 0 to 14, and this is the probability that you saw that many heads if theta is this. Okay? Does that make sense? Now let's look at so that's the first part of the power function. It's just literally this function. This function you can compute numerically, right? You can take theta equals 0.99, and then theta equals 0.98, and theta equals 0.97. So let's start this plot. Here's a plot of theta versus pi of theta. So the most theta we'll get to is 1. Here's 0.9. And when theta is equal to 1, I hope you see this is going to 0. And when theta is equal to 0.9, we actually worked this out, right? What was the size of the, do you remember what it was? It was something like, so here's pi. Pi can go up to 1. Pi will be a probability, or 1 minus a probability. So at 0.9, we had a value of like 0.01 something. We had a very small size in this test. So that's this point. And then from there, it just goes down. So again, I'm just computing this function. I'm summing k from 0 to 14. You do this numerically. 20 choose k. That's some number. Theta is your parameter. This is a function of theta. And the function of theta looks like that. Okay? Now, what do we do? Now what do we do in the complement for theta in H1, i.e. theta is less than 0.9, instead of computing theta, we compute 1 minus beta. Well, what is beta? Beta is the probability of the type 2 error happening. So 1 minus beta is the probability of the type 2 error not happening. So 1 minus beta is the probability of no type 2 error. Well, that's kind of a funny way of saying it. What I really mean is, so what was beta? Is the size of the type 2 error. That means the integral over the complement. The size of the type 2 error is the integral over the complement of the critical region, integrating the likelihood function of the alternative hypothesis in the region theta. And so 1 minus beta, well, the likelihood function is a probability distribution. It's a probability density. And so the integral over something, the integral over all possible outcomes of this thing is one, thank you. Right? And so 1 minus this just changes whether we go from the complement of the critical region to the critical region itself. In fact, that's what we should have done last time in our proof of the Neyman-Pearson lemma. But never mind. I tried to make it even more simple. I fear I didn't succeed. So So 1 minus beta is the probability of L1, the likelihood of the alternative hypothesis, measured over the critical region. So what is that in our case? So 1 minus beta of theta. What's the critical region? Jake. K is less than or equal to 14, so that's a sum as k goes from 0 to 14. And what's the probability of likelihood of the alternative hypothesis? Well, the alternative hypothesis hasn't changed what the distribution is, it just changed what the parameter is. And it says the parameter is less than 0.9. So what is the likelihood of seeing k heads with some theta? Oops. Justin.
L1's a function of theta there, right?
Yes, L1 here is also a function of theta. Thank you. So what's 1 minus beta? What's the difference between 1 minus beta and alpha of theta? Dylan.
The values of theta are always less than 0.9?
It's the values of theta that are different, but the shape of the function itself, it's the same. Okay? That's why this definition for the power function makes sense. Now, that's in this case where we're just checking is a parameter above or below some value. Maybe the distribution, maybe you're testing the distribution, maybe you're testing something else. This function can be quite complicated. Remember, we evaluated it at 0.6. What was the probability of making a type 1 error at 0.6 from your notes from a few days ago? It was 12%. Doesn't matter. It's some number. You can compute this number. 12%, which means the probability of not making a type 2 error instead of 12% is 88%. So 88 is up here. Here's 0.88. 0.6 comes up there. And then there's some shape of the graph like that. So that's the power function. That's the power function of this test. It's literally just this function, for all values of theta, except 0.9 is the place where we would be, this is the region that we're testing. This is where we're computing alpha of theta. And this is we're computing 1 minus beta of theta, but 1 minus beta of theta is the same thing. It's the same function. All that matters is what ranges of thetas we're seeing.
Wait, so what happens when theta goes towards 1?
When theta goes towards 1,
Okay, then that should go to 0.
that goes to 0.
Okay. And then when it goes to 0, that should go.
Yeah. What's the largest value? So I'm getting a little ahead of myself. Let's talk about the likelihood test. Likelihood test. So this is just the power function. Just wanted to explain to you what the power function looks like. 1 minus the power function is often called the operating characteristic. I'll just give you these words. 1 minus the power function. So this is a little bit of a definition. I won't use it, but in case you hear people saying this, you know what it is. The OC curve, which is operating characteristic, or operation characteristic, function, that's what OC stands for, is just 1 minus this curve. In some industries, they use the OC curve. In some industries, they use the power function. This is just for you to know. I'll never test you on this definition. Okay? So what information can you see from this curve? Well, one thing you can see, there's a bunch of things you can see. For example, if you want to test, if you want your power function to be, if you want to choose, once you've drawn this curve, you see that we never used the fact that 0.9 was the null hypothesis and 0.6 was the alternative hypothesis. So you can choose what your null and alternative hypotheses are to get a particular size or power. So the size, if I want to go over here to size 0.05, now I know what value of theta, this is the value of theta for my null hypothesis, that will have power 0.05, that will have size 0.05. Where do I choose my alternative hypothesis to have power 0.05 or 95%? Type 2 error 95. Type 2 error 0.05, which is power 95. So this would be the size 0.05, if that's where I want to choose my null hypothesis to be. So I'm changing now. Once I write down this function, the power function, I can choose the null hypothesis, change the null hypothesis to be from 0.9 to this is the place where I'll get a 0.05 significance, if that's what I want. And if I want a power function of 95, if I want a power of my test to be 95, then this could be my alternative hypothesis. Yes, Jake.
This is all for a specific critical region?
This is all for a specific critical region, yes. So I've chosen, it's a little bit backwards, but I said this last time, that if your test comes out to have too large a power, there's a bunch of things you could do to decrease that power. You can change the critical region, but that will also change the size of the test, typically. You can increase the number of, the n, the number of samples, or you can change what your alternative hypothesis is, or you can change what your null hypothesis is, right? So once you have this function, for a given critical region, you can adjust your null hypothesis and your alternative hypothesis if you're trying to get, 5% and 5% size and 5% power. Okay? That's one thing you can read off the graph right away. Let's get a little bit more into this likelihood statistic in the last couple of minutes. So this was the power function, and 1 minus it is the OC curve. Likelihood statistic, so as we saw, the likelihood function, so L0 of theta is the likelihood function given it's a function of the observation given x1 equals little x1 and xn equals little xn, assuming theta is the parameter size, and theta is this is for theta in H0. In other words, what was the likelihood? So if theta is in H0 in our example, the likelihood of a particular outcome, let's say you saw k coin flips, k heads, was exactly this inner function, n minus k, where n is 20 in our example. Now, how do you maximize? What's the maximum value? So let's call this max L of theta over all theta, over all possible values of theta. Do you remember the maximum likelihood method? We write down the likelihood function. Now, if we're testing H0, then it's only this function for theta is bigger than 0.9. But in general, this is the likelihood of a given output, of a given, whatever our observations were. Our observation is k. K is the observation. Here's the likelihood of this observation for a given value of theta. And we maximize this. We maximize what's the maximum value of theta, for what value of theta, is this maximal. That goes all the way back to our maximum likelihood estimation. Does anybody remember what we proved it was? In other words, you differentiate this with respect to theta. Well, that'll be a horrible mess. It's actually better to take log of this thing, differentiate that with respect to theta, solve for theta equals 0. Does anybody remember what comes out? Other than Ernest? All right, Ernest.
X bar.
X bar, k over n. Right? What's the proportion that should happen? Well, k over n is the proportion that should happen. That's the most likely. So the maximum value of the likelihood over all ranges of theta is the likelihood at the maximal parameter. So let's call this theta hat. Theta hat is the maximal value of theta is k over n. So the max L0 in this case, max L of theta is L of theta hat. In other words, it's 20 choose k, and then k over n to the k, and n minus k over n, which is 1 minus theta, to the n minus k. I'm writing n instead of 20 almost everywhere, so that you see what it looks like in general. But I hope it's clear. So when you see an outcome of k, then this is the maximal, the likelihood at the maximal value of theta over all possible values of theta. In other words, when we look at this curve, this pi curve, well, I mean, we're not seeing the likelihood in this curve. Let me take back what I said, but there's something related. What about the maximal? So let's call this max L0 of theta. This is the maximum over all theta in H0. So let's figure out what this function is. So this is the likelihood this is the largest likelihood that we can see among not all values of theta, but just among those values of theta that are in H0. So what if it just so happens, so if if k over n, if the observed optimal theta, which is k over n, is bigger than 0.9, right? If the optimal parameter theta hat that we observe, k is what we observe. K is how many of the coin flips we actually saw. If k over n, if that ratio is bigger than 0.9, then this optimal value is inside the range of possible optimal values for the null hypothesis. Right? In which case, what is the maximal L value? Well, it's just the original L value. There's no change in the L value to restricting theta to be inside the null hypothesis if the outcome is already consistent with the null hypothesis. Does everybody see that? Let me get through this in the interest of time, and then we'll come back and ask questions. What happens if theta bar, if theta hat, which is k over n, comes out to less than 0.9? Well, now we no longer have, we have a boundary condition instead of having no restriction on theta, in which case we can use the derivative. If the outcome is actually less than 0.9, then the largest likelihood we can get is not the likelihood when we replace theta hat by k over n, but it's the likelihood we get by maximizing this thing over all values in h0. So I want to maximize this function subject to theta hat is at least, this is equivalent to theta is at least 0.9. So what do you think happens to this function? I mean, we can graph this function. If you graph this function, let's just pretend that it looks something like this. So here's a graph of L0. When theta goes to 1, it goes to 0. When theta goes to 0, this goes to 0. And then there's some optimal value in between, and that optimal value happens exactly at k over n. Okay? If it so happens that k over n is bigger than 0.9, then that optimal value is the optimal value here anyway. Then these two agree. But if that optimal value is below 0.9, and I'm restricting the maximum to just the region theta bigger than 0.9, then where is the largest likelihood? At 0.9. So this is the likelihood of 0.9. Let me pull this up. So this ratio, so now I can define the likelihood ratio statistic. Definition. The likelihood ratio statistic is often written lambda, is the maximal value of the likelihood of theta over the values in h0 divided by the maximum value over all possible likelihoods. All values of theta.
Is that a lambda?
That's a lambda. This is a lambda. Okay. So that's the likelihood statistic, and gosh, what can I do? And a critical region for the likelihood test is to capture this thing being bigger than some constant or less than some constant. We're not going to have time for that. All right, we have defined the likelihood ratio statistic. We will return to understanding the usefulness of this statistic after the midterm, but we will not go further in it. In fact, I'm going to take this whole last section and move it to after the midterm. This will not be on your midterm. We're going to come back to the likelihood statistic.